Okay, last time we already discussed about the crystal direction. Uh, Basically, just a vector. Okay, it's a vector in the crystal structure, and the we use Miller indices to identify the crystal direction. Okay, and the direction, the direction and its negative are not equal. Okay, they have different material property, and a direction and its multiple are identical. 100, 200, 300, 400. Okay, those crystal those crystal directions are identical. Okay, and certain groups of the directions are equivalent. Are equivalent. What's that mean? You can see here. This direction is 100, right? Right? And this direction is 010, and they are equivalent. Okay, so we can define. We just shift the coordinates to the different origins, and we can find the same or the identical crystal direction. Okay, for example, this direction and this direction and this direction are identical, right? For example, the crystal direction 110, they have an equivalent group, and we use the spatial bracket, okay, to identify it. And there are 12 directions. 12 crystal directions are identical. For example, if we want to draw the crystal direction 110, what should be in the for example in this unit cell, it should be like this, right? 110, right? It should be 110, right? Okay, so if we look at the unit cell behind this one, if we draw the other unit cell like this, right, the other unit cell, and yes, the identical unit cell, right? This, right? Or this direction. Okay, normal sign. So they are all identical. They are all belongs to the equivalent crystal direction 110. 110. Okay. And the other way to define the crystal direction is repeat distance. Okay, it's repeat distance. Okay, so it is the distance between lattice points along the direction, and it is the other way to classify the direct direction, crystal direction. So what is the repeat distance, which is the distance between two atoms touch? Okay, for example, in this figure shows the and this atom, the center of this atom, and this one, right? These two atoms are touches each other, and this is the repeat distance. Okay, therefore this is the repeat distance, and this is the repeat distance, and this is the repeat distance. Okay, okay, and the other terminology is the linear density, which is the reciprocal of repeat distance. Okay, repeat distance. Okay, and the definition of a packing fraction is equal to the linear density times 2 times atomic radius. Okay, for example, for the 110 direction in FCC copper, what is its packing factor? Okay, what is its packing factor? So we already know the repeating distance of 110 direction, right? We already in the FCC structure, FCC copper, right? Okay, therefore we can figure out its linear density. And we just look up the periodic table. We can find the copper's atomic radius, right? Atomic radius, right? Therefore we can figure out what the packing factor is of the FCC copper. Okay. And next, I'm gonna discuss about this HCP structure. Okay, HCP structure. And now we're gonna use the 4 indices. Okay, the previous slide we used the 3 indices, Miller indices, to identify the crystal directions, right? Crystal direction. And now we can use the 4 indices to define a HCP structure. Okay, HCP structure. Okay, as I already mentioned in this HCP structure, and this plan is called the Basel plan. Okay, therefore we can use the system called the Miller-Bravais indices. Okay, Miller-Bravais indices. Okay, therefore, for the directional indices, which are obtained as that we described earlier, will be denoted by the 4 indices as the U, V, T, W. Well, there are different notation. Doesn't matter. Okay, it doesn't matter. Okay. Okay, it doesn't matter what types of notation you're gonna use. By convention, the first 3 indices that we already mentioned earlier can convert it to the 4 indices. Okay, by convention, the first 3 indices pertain to projections along the perspective A1, A2, A3 axis in the Basel plan. So what is A1, A2, and A3 right here? You see A1, A3, A1, A2, right? And if the 4th indices is the Z-axis right here, the Z-axis. Okay, therefore the convention from 3 indices to 4 index system. Okay, we can summarize. There's a formula by this. Okay, so here the U prong, V prong, and W prong are defined for this 3 index system. Okay, and from this convention, we can from U prong, V prong, and the W prong convert it to the U, V, T, and W. Okay, therefore we came from the 3 index system to 4 index system. Okay, this is a different notation. So this U prime means the A, V prime is B, and the W prime is C. Lattice parameters. Okay. Okay, let's look at the example for this HCP structure, how to define its crystallographic direction. Okay, first the vector represented path through the origin is necessary, if necessary, and read of the projection in terms of the unit cell dimensions A1, A2, A3, and C, or whatever, or Z. Okay. adjust to the smallest integer value and enclose square brackets. Okay. Okay, let's look at the example in the HCP unit cell. Okay. For example, if we have a direction, okay, we have the crystallographic direction, and how to find it, how to define it, right? We have to read out projections in terms of unit cell dimension, right? Therefore, let's look at this figure. This is our direction right here, right? And we have to read out the projection on A1, A2 is A2, right? Projection on A2, right? Is the projection on A1, right? And here is the origin. It's origin. Okay. Therefore, what's the projection of A1? It's 1/2, right? I'm sorry, it's half, not 1/2. It's half, right? It's half right here, right? And what's the projection on A1? It's here, right? And what's the projection on A3? What's the projection on A3? It's -1, right? Can you find its projection? Therefore, we can define its projection on the unit cell direction is half, -1, 0, and we adjust to the smallest integer values and use the overbar. Use the overbar to represent the minus side, so we get a 1, 1, 2 bar 0 for this crystallographic direction in HCP unit cell. Okay, is that okay? Okay, so now I have already mentioned that we can also use this 3 indices conversion to 4 indices. Okay, 3 index system to 4 index system by those equations. Okay. Okay, let's discuss about this plan. In the previous slides, we already mentioned how to find a crystallographic direction by Miller indices. Okay, 3 index system, 4 index system, or in the cubic system, or in the HCP structure, right? Now we have to look at the plan, the crystallographic plan. Okay. Okay, so there are some steps to figure out the crystallographic plan. Oops. Here. Okay, first, identify the XYZ intercepts of the plan in terms of lattice parameters. Okay, if the plan is very important, if the plan passes through the origin must be removed to adjacent unit cell. Okay, I will just show you some examples later. And then take the reciprocal of the intercepts, clear fractions, but do not reduce to lowest integer. Enclose the resulting numbers in parentheses HKL. Okay, so there's the other notation right here for plan. For crystallographic plan is HKL. HKL. Okay, and use the overbar for negative negative numbers. Okay. Okay, so there are some things to keep in mind when you use Miller indices for crystallographic plan. Okay, plans and their negatives are identical. Okay, they're different from the crystallographic direction. And plans and their multiples are not identical. Okay, and each unit cell Plans of a family represent groups of the equivalent plan denoted by this. Okay, and in cubic systems, a direction is perpendicular to a plan if both have the same indices. Okay. Okay, keep those things in mind. Okay, keep those things in mind. I will show you some example. For example, what is this plan? How to define this plan? In the previous slides, we just find out the direction, right? This direction or this direction or this direction. And now we're gonna figure out the specific direction in a unit cell. In a unit cell. Okay, therefore, what's this plan in this unit cell? Right. First, this plan already passed through the origin, right? Therefore, the origin has to be moved to adjacent unit cell. Therefore, this origin has to move to here. Okay. So this is the coordinate system. Okay, therefore, this plan can be figured out, right? Can be figured out. It's 001 plan. Okay. Okay, and this plan in a unit cell, how to define this plan in this system? Okay, and how to define this plan in the unit cell? Okay, I will talk about this in detail later. Okay, give you some examples. First, for the blue one, so this blue one, how to define the crystallographic plan in a unit cell. First, we have to take the intercept 3 lattice parameters. Okay, well, someone will say it's lattice constant. It doesn't matter. Okay, therefore, what's the intercept? What is the intercept on the 3 axes from this plan? Okay, let's look at it. So this is the intercept on x axis, right? And this is the intercept on y, right? And what's the intercept on z direction? Z direction? No, you cannot find, right? That's because this plan is parallel to z direction, right? And to imagine that this is z direction, and this plan is parallel to z direction. Okay, when a crystallographic plan is parallel to an axis, we use the infinity sign to represent this parallel. Okay, therefore, for this plan, it intercept on x-axis, intercept on y, and the parallel to z. Okay, and we take the reciprocal. We are gonna 1, 1, 0. Okay, therefore its middle indices is 1, 1, 0. Okay, it's 1, 1, 0. Okay, the other example is the pink crystallographic plan. How to define it? This plan. So we have to find out the its intercept, right? So it's intercept on x, on x, okay. And is there any intercept on y or z axis? No, right? Cannot find. So this plan is parallel to y and z axis. Therefore, we use the infinity sign. and it's half on x-axis. And take the reciprocal, we got a 2, 0, 0, and 2, 0, 0. Okay, and we can define it, the Miller indices as 1, 0, 0. Okay, we can define it. Just reduce to the smallest we have mentioned here. Okay, clear fraction. Okay. Okay, I have to mentioned here the okay. Okay, let's look at the other example like this. How to define this plan? How to define this plan? We have to figure out the intercepts, right? The intercept on x and y and z, right? So the intercepts is half, 1, and 3/4. And we take the reciprocal. We got a 1, 2, 1, and the and 1/3, right? 1 and 1/3, and reduction is 6, 3, 4. Right? So its Miller indices is 6, 3, 4. Use this Miller indices to identify this plan. Okay, identify this plan. Okay. Okay, so let's look at the crystallographic plan of HCP structure. For example, you can find out this plan. You can find out this plan by using the Miller-Bravis system. Okay, first we have to find out the intercept, the same as the 3 index system. We have A1, A2, I'm sorry, A2, and the A3, right? So this plan has the intercept on A1, right here. And the intercept -1 have an intercept on A3 is -1. It's right here. Just draw it. It's right here, right? It's the A3 and it's the -1. Okay, it's the 1 and it's -1. And for A2, this direction, is there any intercept on A2? No, it's parallel, right? They're parallel, therefore it's infinity. It's infinity. And the intercept on z-axis is right here. It's 1. Okay, therefore we can find the intercept for 4 in this index system is 1, infinity, -1, 1. And take the reciprocal is 1, 0, -1, and 1. Okay, therefore we can figure out that the Miller-Bravis indices is 1, 0, 1 bar 0. Okay, 1, 0, 1 bar 0 represent this plan. Okay, this plan. Okay, therefore the 4 index system HKIL is favored in most instances because it's more clear identify the orientation of the plan in the hexagonal crystal. And for the crystallographic plan, we always also use HKL. right? I've already mentioned this before. Later, I will talk about the XRD, okay? And the XRD system is based on this HKL notation, okay? And there's some redundancy in that the I can be determined by the sum of H and K through this equation. Okay, therefore the way is that, okay, we can find the intercept on this 4 axis, right? On the 4 axis, this is the I right here, right? And I equals to H plus K minus, therefore, I equals to H minus H plus K equals to minus what? 1 plus 0, right? So it's minus 1. So this one is the same as this one. Okay, it's the same as this one. Okay, this is the other way to find out the I, the value I. Okay, so we have already done this. Okay, let's have the other one. Okay, let me ask you a question. Why the I value is 0? From here, from this figure, you can tell why. For this direction, why the I value is 0? Oh, sorry, it's not correct. For this plan, sorry, for this plan, why the I value equals to 0? Why the I value HKIL, right? The intercept of A1, A2, A3, and Z. Why? Any reason? You can think of it. From this example, the K value is 0, right? This plan is K value is 0. Why? Because this plan is perpendicular to A2, right? Perpendicular to A2. The same thing, this plan is perpendicular to A3. Okay, it's parallel to A3, not perpendicular. It's parallel to A3. Okay, in this case, this plan is parallel to A2. This plan is parallel to A2. And in this case, this plan is parallel to A3. Okay. Okay, so give you some examples. How to define this plan? First, this plan already passed through the origin, right? So we have to move the origin to its adjacent plan. You can move to here, or here, or here. It doesn't matter. Doesn't matter. We always can find its plans of family. doesn't matter. Therefore, we move this origin to its adjacent point right here. Okay, adjacent point. Then what else? So we have the new coordinate system here, here, and here, right? Okay, now we have to figure out its intercept. Its intercept with x-axis is here, right? So its value is minus b, right? And the and it's I'm sorry, I have to correct it. Intercept of the z prime axis, sorry, right here. Okay, this plane has its intersect with z prime axis right here. Therefore, it's what? It's half, right? Half of c, half of c. Okay, and what's its intercept of y? It's right here, y. Okay. So what's its projection? What is projection? What is projection is right here, right? So is minus 1b. Okay, it's minus 1b. And what's its intercept on x prime axis? No one, right? Because it's parallel with each other, right? Therefore, this we have to say this plane has the intercept this plane is parallel to z prime axis, right? It's infinity, and it's the intercept of minus 1. It's A, B, and C. Minus 1, and has the intercept of z-axis is 1/2, and we just take the reciprocal of it. It's 1, minus 1, and 2. And it's 0, 1 bar, and 2. Okay. So 0, 1 bar, 2 is defined this plane. It's also defined this plane. Okay. Okay. Let's have a practice of this one. We have a plane here. Okay, it's plane. And we have an origin right here. So how to define this plane? How to define this plane? Okay, so this plane doesn't pass through the origin. Therefore, we don't have to move the origin to its adjacent point, right? So just remember it. Okay. And okay, so what's its intercept? Y-axis? It's right here, right? It's right here. Okay, so what is its intercept on Z? It's right here. Okay, and what is its intercept on X? No one. No one, because this plane is parallel to x-axis, right? X-axis. Okay, so if we define the lattice parameter of this unit cell is A, B, C. Okay, so it's A, B, C. Okay, and this plane is parallel to x-axis. Therefore, we can denote it in infinity. And the intercept on y-axis is what? It's a minus 1. And the intercept on z-axis is 1. Take the reciprocal is 1, minus 1, 1. Okay, and it's 1, 1 bar 1. Sorry, 1, 0, 1 bar 1. Okay, it's this plane. Okay. Okay, so there's an example right here. So what's this plan? If I give you the this plan, okay, for the figure B represents the top view the top view of the figure A. Not top view. It's a top view of certain plant in figure 8. So do you know what's it's crystallographic plan? I'm sorry. So what's this crystallographic plan? Can you define it? Can you define it? Well, obviously it's this plan, right? It's this plan, right? And this plan is what? 110, right? This plan is 110. So what's this structure? Figure A, what's this structure? It's FCC, right? All right, it's already here. So it's FCC structure. Okay, it's FCC structure. Okay. And give you some one example of the family of plants 110. Okay, so there are 12 plants. Okay, there are 12 plants. Okay, there are 12 equilibrium plants of 110. Okay, of 110. You can try to plot. You can try to plot it in a single unit cell. Okay, you can just try to plot it. Doesn't matter. Okay, so next we're gonna talk about the close pack direction, also the close pack plan. Okay, and plan is important for mechanical behavior. Remember, I already mentioned this. The metal, especially for metal and alloy, when you just apply a tensile and just put it till a fracture, you can look at the fracture surface. Okay, you can just observe the fracture surface under any microscope. You will find out it's not a smooth. Okay, it's not a smooth surface. You always fail. You always fracture with certain plane or certain angle. Okay. Okay. And the fracture will occur in the close pack plane and direction. Okay. I will describe this later. Okay, it's quite important for for mechanical engineering. Okay, and there are some other ways to represent these the plans, points, and points, direction, and the plans in a unit cell. Okay, therefore, unit cell can also be considered as being composing of stacking. Okay, of a closed pack plan. For example, for this figure, it shows what HCP structure, right? HCP. So therefore, we have this is called a basal plan. So what's a closed pack plan in HCP? It's a basal plan, right? And this is also the basal plan. So it's a closed pack plan also. And there's the other plan in between, we define as a B plan. And the closed pack plan is A plan. Therefore, for this structure, we can say, oh, it's AB stacking. Okay, if there are two different plans. Okay, two different plans between A, and we can say it's A, B, C, A, B, C, stacking. Okay. Okay. Also the same for this FCC structure, and this is the closed pack plan, right? It's 111 is the closed pack plan. This plan is the closed pack plan, and this plan is the closed pack plan, right? And with a atom here and here. Therefore, it's A, right? And this plan is B, and it's plane C. Okay, it's therefore for the FC structure, it's ABC stacking. Okay. So we can define the unit cell that can also be considered as being composed of the stacking of the closed pack plane. Okay. Okay, so materials property can vary with direction. In this case, it's called anisotropic. Okay, and if the materials property are identical in all directions, the materials is called the isotropic. Okay, it's called anisotropic and isotropic. And for the polycrystal materials, we can consider it as the isotropic. As I already mentioned before, the polycrystal has different size of grain, right? Size of grain. And those grain has the random orientation that can cancel out the anisotropic. Okay, they can cancel out those anisotropic characteristics. Okay. Therefore, remember that the polycrystal materials are effectively isotropic. Okay. How to define the isotropic and anisotropic? Okay. For example, if I apply a force on a metal 1, 0, 0, and I apply 1, 0, 0 direction, and we apply a force on 1, 1, 1 direction. Okay, if their strengths on this direction and this direction are identical, are different, we say it's anisotropic. Anisotropic. If the strengths, the mechanical property, or any properties are identical in the direction of 1, 0, 0 and 1, 1, 1, okay, and these materials can be called isotropic. Okay. Therefore, I give you some examples. Maybe you are interested. So for this wood, it's isotropic or anisotropic. Usually, it's anisotropic. It's anisotropic for wood. You can see the different texture. Okay, different texture. So we apply the force here or from here direction. We apply different force in different direction. They must have different strengths, mechanical strengths. Okay, you must have the different mechanical. And for the silicon, it's isotropic or anisotropic. Of course, it's also anisotropic. Why? Okay, you may say it's polysilicon, but well, we already see the age here, so it is impossible to be a polysilicon. It must be single crystal silicon. Okay, it must be a single crystal silicon. Okay. Well, it's a metal. Of course, some metals are isotropic or anisotropic. It depends. Okay, it depends. Next, we have to define a parameter called the interplane distance, which is the distance between two adjacent parallel planes with the same Miller indices. Okay, so that can be found. It can be found for the cubic materials. Remember that it's a cubic. cubic materials. Okay, so you must remember, you maybe learned this high school mathematics or freshman mathematics. The two planes parallel. We can define this plane use its normal factor, right? And we can figure out the distance between two parallel planes. Okay, the same thing, we can use this math in the interplanar distance. Okay, we define as D is HKL, right? Here is the Miller indices. HKL, and the A naught means the defined as the lattice parameter, right? Because it's a cubic system. It's a cubic system. So this is the lattice parameter. Okay. Maybe I skip this first. I'm gonna jump to the XRD first. Okay, so for the diffraction technique, it's a very important technique to characterize the material's property or material's crystallographic plan. Okay, basically your sample can be a powder or a bulk. It doesn't matter. Okay, it doesn't matter. No matter what, we have to they have to be based on Bragg's law. Okay, based on Bragg's law, and this is the Bragg's law. So? Let's introduce what is Bragg's law. First, we have to consider two waves. Okay, two waves, 1 and 2. 1 and 2. And it's the propagation direction. Okay. And if these two waves are in phase, we saw its constructive interference. Okay, that means the superpose of these two waves, its amplitude is gonna be amplified. Okay, we amplify. Okay, and the other cases is a destructive interference, or we call it out of phase. The same if we have two waves. Okay, and then if we have the same propagation direction, as we superpose these two waves, its amplitude is diminished. Okay, and then we call it as the destructive interference, or it is out of phase. You can see the difference, right? In phase, the amplitude is amplified, right? It's amplified. Okay, and if it's out of phase, the amplitude is decreased, right? It's decreased. Okay, so let's look at the Bragg's law. This plan is HKL. HKL is this plan, and this HKL. And it's the atom here, here, and here. It's the atom here. Okay, therefore this phase is coming out from the screen. Okay, and we have the X-ray just hit the surface. We hit the atom and hit the surface. Okay, and reflect it, and then reflect it. Okay, and let's look at this triangle. This triangle, and the wavelength of the X-ray is fixed. Well, you can find out. You can use the XRD machine to identify its wavelengths. Okay, to identify. Always use copper source, maybe 1.54. Armstrong on that. But it doesn't matter. Okay, it's a constant. Okay, it's a constant. Okay, and the distance passed through from the X-ray passed through, the distance that the X-ray passed through is AB plus BC. Okay, the wavelengths coming in and reflected, coming in and reflected. Okay, coming in and reflected. Okay, therefore we can use this triangle to find out the d-spacing. Okay, to find out the d-spacing right here. It's the interplanar distance between two the same plane. Okay, therefore we can find out the d-spacing from this triangle right here. This is a d-spacing. Is that okay? Okay, therefore the n lambda is the wavelength. Okay, it's the wavelength. The multiple lambda is equals to 2AB because AB equals to BC. Right, and sine theta is equals to AB over D, and we can find out the lambda equals to 2D sine theta. Okay, 2D is a quite simple, right? It's quite simple to figure out the d-spacing from the geometry, right? From the geometry. I think it's not difficult. Right? Okay, so if the diffraction pattern, if the diffraction pattern is in phase, that's mean what? That's mean it follows the Bragg's law. Okay, that's mean it follows the Bragg's law, and the phase should be constructive, right? Constructive. Okay, therefore the incoming X-ray are both and the diffracted X-ray both are in phase. It must follow the Bragg's law. Okay, and if the both are not in phase, the diffracted beam is a near light, right? Therefore, it must not follow the Bragg's law. Okay, in one word is that the diffraction incoming X-ray and the diffracted X-ray are in phase. We can find the constructive amplitude, right? We can detect the amplified amplitude. Okay. Okay. Therefore, for some the machine X-ray machine, for the X-ray machine, we can use the Bragg's law to specify the crystallographic plane. Okay, if this incoming X-ray and this diffracted outcoming or the diffracted X-ray are both in phase, we will find a peak at specific angle. Okay, this is the d-spacing. Okay, we have a detector right here. As the incoming X-ray hit the surface and reflect it, and we'll detect the outgoing X-ray or diffracted X-ray. Okay. When these two X-rays are in phase, that means the two waves are constructive. Therefore, we'll see a peak, sharp peak. Okay, we'll detect the sharp peak right here. Okay, therefore we can find out the despacing. Right here, despacing. Okay, and here the theta, the critical theta here is this angle. It's this angle. Okay, so let's look at the machine right here. Usually we have the sample here. It's our sample. Okay, and it's the instant beam. That means it's the incoming X-ray. Incoming X-ray, and you will bombard heat surface. Right, and some of that will transmit it, and some of it will reflect it. Right, and this is the theta. Okay, here's the 2 theta. Okay, so if this instant beam and this diffracting beam is in phase, we'll find the peak right here. We'll find a peak, right? Diffracted peak. Okay. Okay, so this is the real machine right here. It's a real machine. We have X-ray source to heat the surface, and there's a reflected beam. It's certain will transmit it, right? And the diffracting, we have this detector can rotate it, can scan it with a specific angle. Usually we're from 20 to 90. Okay, always from 20 to 80. So this detector will just scan from 20 to 90. Okay, so you have different diffracted beam, and at a certain 2 theta angle, this 2 theta is right here. It's right here. Okay, at certain 2 theta, some peak will show. That means at this angle, we can find a crystallographic plan. We can find a crystallographic plan, a specific crystallographic plan. Okay, this show you an example. Okay, so this is the data output from the XRD machine. It just will give you, okay, you have a materials after characterized by XRD. We'll see the 2 theta and the intensity. At certain 2 theta, we'll find the specific plan 111 and 200 and the 220 and the 311, 222 and 400. Okay. Okay. The other important things you guys have to learn is that how to find out the information that you really need from this spectrum. From this spectrum pattern. What these peaks tell us. Right? What's the if you cannot use this data, just a piece of junk. Right? It doesn't matter. It's not useful. Okay. Give you an example. We have a diffraction angle 2 theta. Okay, from 20 to, usually we'll just scan the angle to scan this angle 2 theta to 90 degree. Okay. Okay. Oh, we can find the this materials at 45. We can find a plan. The crystallographic plan is 110, and at maybe 65, we can find the plans 200, and at maybe 82, 83 degrees, we find the plan 211. Okay. Oh, so from this diffraction pattern, we know that this material is alpha iron. It's alpha iron. Therefore, we have a database for XRD. It's called the JCPDS. And this database will tell you the information about your XRD pattern, whether the materials you synthesis is matched for this database. Okay, for example, I want to have the alpha iron after cooling. Okay, for example, as from the high melting temperature to cool down to certain temperature will transform to alpha iron, right? Okay, I want to know whether my process is correct or not. Okay, I can do the XRD characterizations, and after that, we can look for this database. If the XRD spectrum, what we have done, is identical, it's the same as that in that database, and we can confirm that. We can confirm that, oh, this material's ion synthesis is alpha iron. Okay, is alpha iron. Okay. Therefore, the XRD is one of the powerful technique to characterize materials. Okay. Okay, so today's course will be ended here. So see you next week.